This is the second session on normal distribution. And in this session, I would like to demonstrate the normal distribution applications. The one which is to fit the data for a normal distribution so that we become able to get the estimates of probabilities from the table, from the normal distribution table. Secondly, there is the modality of a normal distribution that for some problems like the fatigue lifetime, the original x is not normally distributed. However, if we take the log of x variable, then it is converted to a normal distribution. The distribution becomes normal distribution. So that is going to be the second modality. And also, there is going to be the third modality, like I mentioned in the earlier session, that the binomial processes for very large number of trials can also be estimated by the use of normal probability distribution table. So let's look for the fitting of the data. So here I have adopted a problem from the book by Professor William D. Corsi. So the thickness of a particular metal part of an optical instrument on 121 successive items from a production line are given. And for these 121 values, the estimated mean value is 3.369, and the standard deviation, where S signifies that it is a value from the sample. We will later on explore that a sample of size 121, it is it's a it's a reasonable representative of a population. So therefore, S and sigma are not going to make any difference in calculations. So for this distribution, let's assume that the thickness of metal parts conforms to normal distribution about the mean value x bar. Well, this is also to signify that it is a sample. And also well, it's a normal distribution. Let's assume for the time being, we have no other we have just calculated these two. The two calculations can be done irrespective of the distribution of the data. So let's assume, without applying any test, the test of distribution fitting, that the data is normally distributed. So we have just calculated two values from a formula, and we are assuming that. So if this assumption is true, then, for example, if I try to calculate the probability of getting a value from 3.2. So I would like to get the estimate of probability that the value lies between 3.21 to 3.42, which means what fraction of values belong to this interval. So let's perform these calculations from, well, this is a very nice kind of, these are very nice kind of points. 3.21 is smaller than the mean value, and 3.42 is greater than the mean value. So let me demonstrate the procedure. So I will get to the Microsoft Excel sheet. So I have selected 3 point. So x1, I select x1 value, which is 3.21, and x2 value is going to be 3.42. So well, I have to calculate the values. So I will calculate the corresponding z values, z1 and z2 about the for x1. So it will be equal to the x value minus the mu value, which is 3.369 divided by 0.0629, which is the standard deviation value. So it's a negative value. And then for this one, okay, so let me see whether it has been rightfully calculated or not. Yes, so it has picked the K4 value. So I have to calculate the probability from x1 to x2, which is correspondingly from z1 to z2. So okay. So I mentioned earlier and that we will change the scale. So it is the x scale. We have 2 points x1 and x2, and they are um, on the opposite sides of the mean value. So we would like to consider the probability that x1 is less than or equal to x, less or equal to x2. So this needs to be calculated as an integral from x1 to x2 of the continuous distribution dx. So, and this is going to be equal to when we see that one on the transform domain Z. So x1 corresponds to a value z1 and x2 corresponds to a value z2, and the mean value corresponds to a z mean value, mu z is equal to 0. So our integral or our probability will be likewise converted to the corresponding z values. So from z1 to z2, and this is going to be from z1 to z2, and the standard normal distribution function. So we recall that phi of z was an integral from minus infinity to a z value and of the standard normal distribution. So in our case, we have z2 value, a higher value. So it's going to be like this one, that we have a z2 value higher. So the phi of z2 will give us the whole region, area under the curve, from minus infinity to z2 value. And we will then see that z1, so it is going to be the area which I have now marked as with the uh, red lines. So from z1 to z2, it seems that it can be written as minus phi of z2 of dz dz minus uh, the area to z1 dz dz. And this is then phi of z2 is probably the area under the curve from minus infinity to z2 value and minus phi of z1. So this needs to be estimated. So in the Microsoft Excel sheet, there is a function available to calculate these values. So I will calculate normal dot standard dot distribution. So there was very interesting information right there. It returns the standard normal distribution has a mean of 0 and a standard deviation of 1. Uh, so then there are two functions. So it only requires z to be provided. So I pick up this value from here. Okay. And then I have two options, cumulative, true for cumulative and false for probability density function. So we are looking for phi z, which is the cumulative distribution function. So I would say true. So this is 0.0057. So let's check this value from our table, minus 2.52. So from the table. Yeah. So here is the table, minus 2.52. So 2.528. Well, I can go up to two decimal places. So minus 2.5. So here I can move to 0.3. So it is 0.0057. So over here in the two lines. So I can mark the point 2.5, and so here is the point that I can mark. So 0057. So the Excel demonstration is consistent with the convention from the book. Okay. So likewise, I will calculate phi of z2. So this is a matter of repeating the calculation. So this value refers to normal distribution function cumulative to 0.81, so 0.7913. Let's see that one from the book as well. So it is going to be on the second page with the positive values. So 0.79. So 0.79, not 0.79. I have to see the probability against the z2 value, which is 0.81. Okay, so here it is. Here it is. I can see a value. So 0.8 and 1. So it is over here, it is 0.7910. 0.7910. So we have got these values. So now the area or probability from x1 to x1. So I say probability of the desired region. This will be the phi z2 minus phi z1. So there is about 78.55 percent components that will belong to that that interval. So the interval we selected. So there is a probability that we have just calculated, and yes, 0.78, more than 0.78% probability that the value falls from 3.21 to 3.42. If the distribution of the data belongs to normal distribution about this mean value and a standard deviation of 0.0629. So later on, we will figure out that we will study that from one sample to the other sample, if the differences are there, so how do we compare them? So to fit the data for a normal distribution, the first step is to generate the probabilities from the model distribution about mean value and standard deviation. Here is the example. So the x lower limit and the x upper limit. Here is the x bar, which is the development, which is the class mark, and this is the FO is the observed frequency. So this is for this problem. This is the process of generating a frequency distribution, and then the estimate of relative frequency has been generated. So the relative frequency refers to the relative prevalence of the objects in lower limit and the upper limit. So then we have to generate the same relative frequency or the probability if the model is built about the parameter of a distribution. Like in this case, we have to generate the model predicted probabilities using this mean value and this standard deviation. So for every x value, we will generate the lower limit in z scale and also the upper limit in the z scale. And we will generate the probabilities by the process I mentioned just before this example. From this example for my two values. So we will calculate the probabilities for every class. And then if we'd like to get the estimate of frequency, so the probability is converted to frequency by multiplying this probability with the total number of objects, which is in this case 121. So generation of probabilities for every class. So if we carry out these calculations, so we can generate this type of a frequency comparison graph. So sometimes the thickness is plotted on x-axis and frequency on the vertical axis. So well, this is also a kind of similar representation. Here we have chosen the thickness of the variable on z-axis and frequencies on the x-axis. However, in this case, this is to be considered as the independent variable. So expected frequency is shown with the red colored bars and the observed frequency with the blue bars. So now at some points they are quite close and at some points they are different. So there is going to be a less than 100% confidence for saying that the data conforms to a normal distribution. Like the expected refers to the estimates generated from probability model, which was built around the data mean and standard deviation values, whereas the blue are the real experimental frequencies. So there are hypothesis testing methods and methodology which help us to say with how much confidence interval we can say that this data can be modeled as a as a standard normal distribution about this mean value and the standard deviation. So the detailed discussions in Microsoft Excel, they have been given in a video link which is provided over here, and I will drop this link in the description of this video. So the next modality, which is a one step ahead of it, which is a again an application of this one, normal distribution. So some variables x, they when converted to log, so they generate a new variable y, which is normally distributed. So the calculation of x and probabilities, they are first converted to x variables, and the probabilities are generated for y limits, and then they are interpreted for x. Similarly, some distributions, some variables, when transformed to 1 over x, they become a new variable which is normally distributed. The log normal distribution has special applications. We have one example in this session as well. So sometimes x raised to the power 1 by 2, and sometimes x raised to the power 1 by 3. So a log normal distribution is a useful one where the log of x variable is normally distributed. Then we say the x is log normally distributed. So the log normal distribution's probability density function is similar to normal distribution. However, we can notice that there is some extra x over here as compared to the normal distribution expression. And also, instead of x appearing in the over here, we have log natural of x. If we see the plots of distribution function, density function, so it is going to have a sharp peak, which means larger frequency towards the lower values, whereas the smaller number of observations are going to be for larger values. The cumulative distribution function is a monotonically increasing function which saturates up to 1. For the log normal distribution, it is applicable to the processes where x is only going to have the positive values. So this is, of course, due to the mathematical limitation for the logarithmic function. So the typical engineering applications of log normal distributions are fatigue lifetime measurements and estimations, fatigue lifetime estimations, the grinding process, and the concrete containment failure modes. They are studied with the help of log normal distribution. So, for example, from the book by Professor William D. Corsi, there is an example. The size distribution of particles from a grinder was measured using a scanning electron microscope. The size distribution as cumulative percentage of number of particles as a function of particle size in millimeters is given below. So we would like to see the probabilities according to the log normal distribution. So we will convert this variable to log of x equal to y. Then we will estimate the probabilities corresponding to the x values. However, we will be using the same normal distribution table. So I have copied this data to Microsoft Excel sheet. Okay, so this is here. So particle size in millimeter, and we have these values, and of course we have these limited number of observations. So around, well, these are the 12 observations. So their relative frequency is provided in percentages. So it seems to saturate. Yes, it must saturate to 1. So if we would like to see the observed probabilities, so we can say the observed probabilities. The observed probabilities. So these are just all these values divided by 100. So we will first transform the variable to y. Here we are assuming that the particle size x is log normally distributed. Therefore, the variable y, which is defined as log of x, will be normally distributed. So I define the natural log of x values. So these values have been generated. So we are assuming that the new variable y is normally distributed, so that a log normal distribution is valid for x. So so far we have not mentioned any test for confirming this thing, or to accept this one with a certain margin. So I calculate the mean value, since these are just the 12 observations. So I can calculate a simple average value of the new variable. So average value, and I require a standard deviation. So STD, I can calculate the standard deviation. STDED, that's the function. And for sample, estimate standard deviation based on sample. So the important thing that we are getting, we are calculating all the estimates for the transformed variable. So we got these two values. So it means a normal distribution in y should be generated around this mean value and the standard deviation. So now if this is fine and valid, so what is the probability that the value of x is between x1, for example, I'll take a value 25 and a value, okay, 25, and x2 value is say 40. So how much percentage of values belong to this interval? So I will calculate correspondingly the y values. So y value is log of this one, and similarly log of this value. So now the two values have been generated. In order to calculate the probabilities from normal distribution, I will generate the corresponding z values. So z values will be the y value minus the mean value of y. So $6 and divided by $7. So the z value is being calculated, and then I will calculate the z value for the other, and then there is going to be the standard calculation, normal standard distribution, and for this z value and cumulative true. So this value has been generated, and then a value for this one, and the required probability that the value belong to the interval of x. So Correspondingly, this value will be the height value minus the load value. So it is 0.17254. So 17% of the components, they will 17 components, 17% of the components, they will have particle size from 25 millimeter to 40. So that's the way we use the normal distribution table in all other distributions in which there is a mathematical transformation consistently applicable. So I will dedicate another session to demonstrate the third modality of the normal distribution, which is its its usage for binomial distributions in the cases where the number of trials are very large.